Today, we're going to talk about something so basic, so fundamental, that you're probably using it right now without even thinking about it. We're talking about sets. It's really just a powerful way of thinking that helps us turn chaos into order, find patterns, and, believe it or not, solve some pretty tricky problems. I mean, that's a huge question, right? Every single day, we are just bombarded with information, with objects, with ideas, people. So, faced with all this stuff, our brains have come up with this really clever, almost automatic way to handle it all. And that's it. That's the big secret. We do it all the time. We group our music into playlists, our contacts into family and friends, our groceries into fruits and vegetables. This basic human instinct, it's the foundation of a whole field of mathematics called set theory. So let's put a formal name on this idea and give it a few ground rules. We're not really learning something new here. It's more like we're learning the official language to describe something our brains already do naturally. Okay, there's the official definition. And the most important part of that sentence is well-defined. All that means is that there has to be a crystal clear rule for whether something belongs in the group or not. There's no maybe. For any object you can think of, the answer to, hey, is this in the set, has to be a definite yes or a definite no. So, for instance, a set can be just a simple list of odd numbers, like set A. Or it could be a collection of names, like you see in set X. It could be all the vowels in the English alphabet, like set V. Or, and this is pretty cool, it can be defined by a rule, like set B, which is the set of all even integers. I mean, that's a list that literally goes on forever. All right, so once we start making these groups, we pretty quickly notice that some groups fit completely inside of other bigger groups. And this relationship, well, it turns out to be incredibly important. So the key word to lock onto here is every. For set A to be a subset of set B, you have to be able to check every single thing in A, and every single one of them has to also be in B. If even one little element from A isn't in B, then nope, it's not a subset. Let's make this super clear. Just imagine all the students in your school. That's one big set, right? Now just think about the students in class 11. That's another set. Well, since every single student in class 11 is also a student in the school, the class 11 set is a subset of the whole school set. It's as simple as that. And you can see this idea beautifully with the numbers we use every day. The set of natural numbers, your basic counting numbers, 1, 2, 3, that's a subset of the integers, which also brings in 0 and all the negatives. And the integers are a subset of the rational numbers, which includes all the fractions. And all of those are subsets of the real numbers. It's like a set of Russian nesting dolls, where each one fits perfectly inside the next bigger one. Okay, so we know how to make sets, and we can see how they fit inside each other. The next logical step is to start doing things with them. This is where sets stop being just lists and start becoming a real tool for sorting and figuring things out. First up is the union, which has this U symbol. The easiest way to think about this is as the OR operation. If an element is in set A or it's in set B, then it gets invited to the party. It's all about combining the groups into one big supergroup. Now, this little detail is absolutely critical. When we combine the two sets, if something is in both of them, we only list it one time in the final union. You don't double count. Think of it like building a team of unique members. Next, we've got the intersection with that upside-down U symbol. Now, if union is OR, then intersection is definitely AND. To get into the intersection, an element has to be in set A, and it also has to be in set B. We're not combining here, we're looking for that exclusive shared territory, the overlap. And this slide just lays it out perfectly. Look at the union on the left. We just scooped up all the numbers from both sets, but notice 6 and 8 are only listed once. Now look at the intersection on the right. The only numbers that were in both A and B were 6 and 8. That's the overlap. And finally, there's the difference. A minus B is pretty much what it sounds like. You start with everything inside set A, and then you just take out anything that also happens to be in set B. You're left with only the stuff that is uniquely in A. Now, all these cool operations, union, intersection, difference, they're great, but they only really make sense if we first define the boundaries of our world. We have to set up the playing field before we can start the game. And that's where the universal set comes in. We usually show it as a big U. Now, this is not the actual universe with planets and stars. It's just the master set for whatever problem you're trying to solve. So if we're talking about students, the universal set might be all students in the entire school. It's the background for everything else we're doing. So once you've defined your universal set, you can then talk about the complement of any set inside it. The complement of A, which we write as A prime, is just everything in that universe that isn't in A. You can just think of it as the everything else pile. All right, we've got the definitions, we've got the operations. So let's see how these tools actually work in the real world by tackling a puzzle. This is where the rubber meets the road. So here's our situation. We've got a survey of 400 students. We know a little bit about their juice preferences. And the question is simple. How many of these students don't drink either one? Okay, first step is always to translate the words into the language of sets. So the total group of 400 students, that's our universal set, U. The 100 students who drink apple juice, that's set A. The 150 who drink orange juice, that's set B. And that keyword both, the 75 students who drink both, that's our intersection, A intersect B. So how do we get the answer? Well, first we need to figure out how many students drink at least one juice. That's the union. The formula for that is the number in A plus the number in B minus the number in their intersection. We have to subtract that intersection because otherwise we double count those 75 students. So that gives us 175 total juice drinkers. Now for the easy part, to find out who drinks neither, we just subtract that number from our total universe of 400 students. And boom, there it is, 225 students. That's our answer. 225 students were taking neither apple juice nor orange juice. By just organizing the info into sets and using one simple formula, we cut right through the noise and found a clear, definite solution. So, as you can see, sets are way more than just a math concept. They are a system for organizing information, for bringing clarity. Whether it's your music library, your friends, or market research, the principles are exactly the same. Define your groups, figure out how they relate, and use that clarity to answer interesting questions. So the only question left is, what are you going to organize first?